Picture the night sky above you right now. Stars scattered like diamonds across velvet darkness, each one a sun burning in the cosmic deep. They appear motionless, eternal, fixed in their ancient patterns. But this stillness is an illusion born of distance and the brevity of human lifetimes. In truth, everything moves. The star we call our sun races through space at 220 kilometers per second, carrying its family of planets in a grand orbital dance around the center of our galaxy. That galaxy itself spins like a cosmic pinwheel, its spiral arms sweeping through space at velocities that dwarf our fastest rockets. Beyond our Milky Way, countless other galaxies rush away from us in the expanding fabric of space-time itself, their light stretched red by the vast distances they cross to reach our eyes. This is the universe we inhabit, a cosmos in perpetual motion, where nothing truly rests, where everything follows the ancient choreography of gravity and momentum that began with the Big Bang itself. For billions of years, this cosmic dance has proceeded according to precise mathematical laws. Planets orbit stars in predictable ellipses. Comets sweep their elongated paths around the sun, returning with clockwork regularity. When objects venture between the stars, they follow trajectories we can calculate with extraordinary precision, their speeds determined by the gravitational wells they've escaped and the forces they encounter along their journey. These interstellar wanderers typically race through space at breathtaking velocities, anywhere from 26 to 87 kilometers per second. That's fast enough to cross the diameter of Earth in less than 8 minutes. They move this quickly because escaping a star's gravitational embrace requires tremendous speed, and once free of that cosmic anchor, nothing in the nearly perfect vacuum of interstellar space can significantly slow them down. We learned this truth in October 2017, when humanity encountered its first confirmed visitor from another star system. The object appeared first as a point of light in the survey images from the Panoramic Survey Telescope and Rapid Response System in Hawaii. Astronomers initially mistook it for an asteroid, then briefly thought it might be a comet before realizing something extraordinary. Its trajectory was hyperbolic, not elliptical. This meant it wasn't bound to our sun. It had come from somewhere else entirely. They named it Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first. And like a scout, it behaved exactly as our understanding of physics predicted. It entered our solar system at precisely the speed expected for an object that had escaped the gravitational influence of another star. It accelerated as it approached the sun, slingshot around our star's gravity well, then decelerated as it climbed back out toward interstellar space. The trajectory was textbook perfect, at least initially. 2 years later, another visitor arrived. This one announced itself more dramatically, glowing with the unmistakable signature of sublimating ice as it neared the sun. Astronomers named it 2I/Borisov after its discoverer, and watched as it too followed the laws of celestial mechanics with mathematical precision. It was clearly a comet from another stellar system, its nucleus vaporizing in the sun's heat, creating a beautiful tale that confirmed our models of how such objects should behave. Both visitors had done exactly what interstellar objects were supposed to do: arrive fast, pass through quickly, and disappear back into the cosmic dark, their paths bent but not broken by our sun's gravitational influence. Then came the third visitor. The Asteroid Terrestrial Impact Last Alert System, ATLAS, first detected it in January 2025. The automated sky survey, designed to spot potentially hazardous asteroids, flagged the object as unusual almost immediately. Like its predecessors, it was clearly interstellar, following a hyperbolic trajectory that would take it through our solar system and back out into the void between stars. But this visitor was different in ways that would soon challenge everything we thought we understood about objects travelling through space. 3I Atlas was larger than Oumuamua, more massive than Borisov, and appeared remarkably stable as it approached the inner solar system. No comet-like outgassing, no tumbling rotation, no signs of structural breakdown under the sun's increasing heat and radiation. It seemed, in many ways, like the perfect interstellar traveller, a solid, intact object, making its way through our cosmic neighbourhood with the stately dignity of a ship passing through harbour waters. Initial measurements confirmed what astronomers expected. The object was travelling at approximately 43 kilometers per second relative to the Sun, well within the range predicted for an escaped planetary fragment or rogue asteroid from another star system. Its trajectory showed the subtle bending expected from solar gravity, its path curving slightly as it passed through the gravitational influence of our star. Everything was proceeding according to the immutable laws of celestial mechanics. Then the measurements began to change. At first the changes were subtle, variations so small they fell within the margin of observational error. Perhaps the object's velocity was 39 kilometers per second, not 43, then 35, then 31. Each new observation session revealed the same impossible trend. The visitor was slowing down. The precision required to detect such changes across the vast distances of space is extraordinary. We're talking about measuring velocity changes of mere centimeters per second across billions of kilometers, like detecting the slowdown of a racing car by watching it from the moon. Yet multiple observatories confirmed the same unsettling reality. Our third interstellar visitor was gradually, steadily, inexplicably losing speed. This shouldn't happen. In the near-perfect vacuum of space, with no atmosphere to create drag, no significant particles to collide with, nothing should be able to slow down an object travelling between the stars. The laws of physics are clear on this point. Objects in motion stay in motion unless acted upon by an external force. But here was an object that appeared to be forgetting this fundamental rule of the universe. Astronomers checked their instruments, recalibrated their measurements, and ran calculations again and again. The result was always the same. The visitor was decelerating in a steady, consistent pattern that defied conventional explanation. It wasn't tumbling or fragmenting. It showed no signs of outgassing or collision. It simply seemed to be choosing to slow down. The implications sent ripples of excitement and unease through the astronomical community. If an interstellar object could spontaneously decelerate in the vacuum of space, then either our understanding of physics was incomplete, or this particular object was not behaving naturally at all. Night after night, as Earth rotated and carried observers around the globe, telescopes tracked the visitor's progress across the sky. And night after night, the measurements confirmed the impossible. Here was something that had travelled the vast emptiness between stars, only to slow down as it passed through our solar system. Now, in a universe where everything moves according to predictable laws, where galaxies spin and planets orbit and comets race along their appointed paths, we had discovered something that was breaking the most fundamental rule of all: the conservation of momentum in the vacuum of space. The question that haunted everyone who studied the data was both simple and profound. What could cause an interstellar object to slow down when nothing in space should be able to stop it? Was this visitor revealing physics we had yet to discover, hidden forces that operate in the darkness between stars? Or was it demonstrating something even more unsettling? That not everything wandering through our cosmic neighbourhood is entirely natural. As our mysterious traveller continued its impossible journey, gradually losing speed with each passing day, it carried with it a challenge to everything we thought we knew about motion in the universe, and perhaps, just perhaps, it carried something else as well. The first sign that the space around our solar system might not be as empty or as natural as we had always assumed. Have you ever wondered if the universe might be trying to tell us something through the objects that visit us from the deep? What would it mean if this visitor's slowdown wasn't an accident of physics, but a deliberate signal meant to capture our attention? The answer to that question would require us to examine the very foundations of motion itself, to understand why the deceleration of a single object could shake our confidence in the laws that govern all of existence. Because in a cosmos where everything moves, the presence of something that chooses to slow down changes everything we thought we knew about the nature of space, time, and the possibility that we're not alone in our cosmic dance. To understand why a slowing interstellar visitor should be impossible, we must first journey back to a winter evening in 1687, when a brilliant mind in England penned 3 simple sentences that would forever change how we see the universe. Sir Isaac Newton, sitting by candlelight in his study, wrote what we now call his first law of motion. Every object persists in its state of rest or uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it. In those carefully chosen words lay a truth so fundamental that it governs everything from the flight of birds to the orbits of planets to the wandering paths of interstellar visitors. Objects in motion stay in motion. Objects at rest stay at rest. Change requires force. This isn't merely theory, it's the bedrock upon which we've built our entire understanding of the cosmos. Every spacecraft we've ever launched, every planetary orbit we've predicted, every comet's return we've calculated, all rest on this simple, immutable principle. Imagine for a moment throwing a ball on Earth. It arcs through the air and falls to the ground, slowed by air resistance and pulled down by gravity. But imagine that same throw in the perfect vacuum of space, far from any gravitational influence. That ball would travel in a straight line forever, never slowing, never stopping, maintaining exactly the same velocity it had the moment it left your hand. This is the reality of interstellar space, a realm so empty, so devoid of matter, that it approaches the theoretical perfection of absolute vacuum. Between the stars there is almost nothing, perhaps one atom for every cubic centimetre of space, sometimes even less. To put this in perspective, the air you're breathing right now contains about 25 trillion molecules in that same volume of space. In such emptiness, there is nothing to slow down a travelling object, no air to push against, no ground to scrape across, no medium to create drag. An object moving through interstellar space should maintain its velocity with mathematical precision, its speed as constant as the fundamental constants of physics themselves. Yet here we find ourselves contemplating an object that seems to have forgotten this most basic rule of existence. The mathematics of interstellar travel are both elegant and unforgiving. When an object escapes the gravitational well of a star, it must achieve what we call escape velocity, the precise speed needed to break free from that star's gravitational embrace. For our Sun, that speed is about 11 kilometers per second. But most interstellar objects are travelling much faster, having been accelerated by gravitational encounters or stellar processes that flung them into the cosmic deep at tremendous velocities. These speeds are not arbitrary. They're determined by the energy required to overcome gravity, the same force that keeps planets in their orbits and holds galaxies together. Johannes Kepler discovered the mathematical relationships that govern these orbital dances centuries ago, describing how objects move in elliptical paths around massive bodies, how their speeds change as they approach and recede from their gravitational anchors. When we apply Kepler's laws to interstellar visitors, we get hyperbolic trajectories, open curves that bend around our Sun but never close into ellipses. These objects approach from the depths of space, accelerate as they fall toward our star, whip around the Sun's gravitational influence, then decelerate as they climb back out of the solar system's gravitational well. But this deceleration is perfectly predictable, caused entirely by the Sun's gravity pulling them back as they retreat. What we observed with our mysterious visitor was something altogether different. The deceleration we measured was far too strong to be explained by solar gravity alone. At the distances where we first detected the slowdown, the Sun's gravitational influence was negligible, not nearly powerful enough to account for the steady loss of velocity we were witnessing. It was as if the object was fighting against an invisible force, something acting upon it that our telescopes couldn't detect and our physics couldn't explain. Consider the forces that can actually affect motion in the vacuum of space. Gravity is the most obvious, the warping of space-time around massive objects that pulls other objects toward them. But gravity always attracts. It doesn't typically slow down objects travelling away from its source. Solar radiation pressure is another possibility. The gentle push of photons from the Sun can indeed affect small objects over long periods. But the calculations were clear. Radiation pressure from our star was orders of magnitude too weak to account for what we were seeing. Could the object be interacting with the solar wind, that stream of charged particles flowing outward from our star? The measurement suggested not. The visitor showed no signs of electrical charging, no plasma interactions, no magnetic field disturbances that would indicate such an encounter. What about the interstellar medium itself? Those sparse atoms scattered through the space between stars. Even in the densest regions of the galaxy, this material is so thin that it would take millions of years to slow down a massive object by any significant amount. Our visitor was losing speed on timescales of weeks and months, not geological ages. One by one, we eliminated the known forces that operate in space, and one by one, they proved insufficient to explain what we were witnessing. This left us with only two possibilities, each more unsettling than the last. The first possibility was that our understanding of physics is incomplete. Perhaps there are forces operating in interstellar space that we haven't discovered yet. Mechanisms of deceleration that work on scales or in ways we've never encountered. This wouldn't be the first time the universe has surprised us with new physics. Dark matter and dark energy, which together make up 95% of the cosmos, were completely unknown to science just a century ago. But the second possibility was even more provocative. Perhaps the deceleration we were witnessing wasn't natural at all. In our own exploration of space, we've developed sophisticated methods for changing a spacecraft's velocity. We use rocket engines to accelerate and decelerate, gravitational slingshots to alter course, even the gentle pressure of solar sails to provide propulsion. Every one of these techniques requires energy, planning, and deliberate control. What if our interstellar visitor was demonstrating similar control? The steadiness of the deceleration suggested something more than random physics. Natural forces tend to be chaotic, variable, subject to the countless small influences that make prediction difficult over long periods, but the velocity changes we measured were remarkably consistent, following a pattern that looked suspiciously like the controlled burns of a spacecraft adjusting its trajectory. This raises a question that pushes us to the very edge of our comfort zone as scientists and as human beings. If this object is slowing down deliberately, then what is its purpose? Objects that slow down are objects that intend to linger, to study, to stay longer than natural trajectories would allow. The possibility that we might be observing our first example of extraterrestrial technology isn't one that astronomers entertain lightly. The scientific method demands extraordinary evidence for extraordinary claims, and the burden of proof for such a conclusion is appropriately high. But when conventional physics fails to explain what we're seeing, when every natural force proves inadequate to account for the observations, we must consider alternatives that challenge our assumptions about what's possible in our cosmic neighbourhood. There's something profoundly unsettling about watching an object break the fundamental rules of motion. It's like watching a dropped stone fall upward, or seeing a clock run backward. The laws of physics aren't just academic abstractions, they're the foundations of reality as we understand it. When something appears to violate those laws, it forces us to question everything we thought we knew about how the universe works. Newton's first law isn't just a description of motion, it's a statement about the nature of existence itself. In a universe where objects in motion stay in motion, the presence of something that chooses to slow down represents a fundamental challenge to our understanding of what's natural and what's not. As our mysterious visitor continues its impossible journey, gradually losing speed with each orbit around the Sun, it carries with it more than just the mystery of its own deceleration. It carries the weight of a question that could reshape our understanding of physics, of technology, and of our place in a universe that might be far more actively populated than we ever dared imagine. The ancient Greeks believed that the heavens were perfect and unchanging, that celestial objects moved in perfect circles according to divine mathematics. We've learned since then that the universe is far stranger and more dynamic than they imagined. Planets follow elliptical orbits, stars explode and collapse, galaxies collide and merge in cosmic violence that spans millions of years. But through all these discoveries, one principle has remained constant. Objects in space follow predictable laws of motion, until now. What happens to our understanding of the cosmos when we encounter something that refuses to follow those laws? What does it mean when the universe presents us with an object that seems to possess agency, intention, the ability to choose its own path through space? The answer to these questions lies not just in understanding what forces might be acting upon our visitor, but in confronting the possibility that those forces might not be forces at all. They might be choices. And if that's true, then we must ask ourselves, what kind of intelligence would travel across the vast emptiness between stars, only to slow down when it reaches our solar system? The laws of motion that have guided us for centuries may be about to teach us something new, not about how objects move through space, but about who or what might be moving them with purpose through the cosmic dark. When faced with the impossible, scientists do what they do best. They systematically eliminate the possible until only the truth remains, no matter how uncomfortable that truth might be. The deceleration of our interstellar visitor demanded explanation, and the astronomical community responded with the methodical precision that has guided scientific inquiry for centuries. Every known mechanism that could potentially slow an object in space was examined, tested, and measured against the observations. One by one, these explanations revealed their inadequacy, leaving us not with answers, but with a deepening mystery that challenged our fundamental understanding of what's natural in the cosmos. The first and most obvious explanation drew from recent experience with our previous interstellar visitor. When Oumuamua had shown unexpected acceleration as it departed our solar system, scientists eventually proposed that outgassing, the sublimation of ice and other volatiles from the object's surface, was providing tiny but measurable thrust. Like a natural rocket engine, jets of vaporizing material could push against the object, altering its trajectory in ways that pure gravitational mechanics couldn't account for. It was an elegant solution that satisfied both the observations and our understanding of how comets behave. Even though Oumuamua showed no visible coma or tail, the theory suggested that small amounts of gas escaping from its surface could create the acceleration we measured. But our current visitor presented the opposite phenomenon: deceleration, not acceleration. Could outgassing still be responsible? The spectroscopic analysis was unambiguous. When telescopes examined the light reflected from the object's surface, they found no trace of the water vapor, carbon monoxide, or methane that typically accompany sublimating ice. No infrared signatures of warming volatiles, no ultraviolet emissions from excited gas molecules, no radio signals from molecular transitions. The electromagnetic spectrum remained stubbornly silent across all wavelengths that might indicate active outgassing. More tellingly, the object showed no visible jets, no coma, no dust trail that would indicate material streaming away from its surface. Even the most sensitive observations revealed a pristine, unchanging appearance as it journeyed through the inner solar system. If gas was escaping from this visitor, it was doing so invisibly and undetectably, a scenario that stretched plausibility beyond the breaking point. But perhaps more fundamentally, outgassing typically accelerates objects, pushing them away from the source of heat that drives the sublimation. To create deceleration, the jets would need to be pointing forward, acting like retro rockets slowing the object's forward motion. The geometric requirements for such an arrangement, combined with the complete absence of any detectable outgassing, made this explanation untenable. The second avenue of investigation focused on collisions and fragmentation. Could our visitor have struck something during its journey? A piece of interstellar debris, a rogue asteroid, perhaps fragments from an ancient stellar collision? Such an impact could potentially knock pieces off the object, reducing its mass and creating the appearance of deceleration when measured against its original trajectory. The search for evidence was exhaustive. High-resolution imaging revealed no change in the object's brightness or apparent size, no debris field trailing behind it, no dust clouds that would indicate recent fragmentation. Spectroscopic monitoring detected no new absorption lines that might suggest fresh material exposed by impact damage. The visitor maintained its steady appearance and consistent electromagnetic signature throughout its passage, showing no signs of structural change or material loss. Moreover, detailed calculations of the impact energy required to produce the observed deceleration revealed an uncomfortable truth. Any collision violent enough to significantly slow such a massive object would have shattered it completely, scattering fragments across interstellar space. The fact that our visitor remained intact while somehow losing speed eliminated collision scenarios from consideration. The third possibility centered on the Yarkovsky effect, a subtle but measurable force created when objects absorb sunlight and re-radiate that energy as heat. This thermal emission creates a tiny thrust force, like an incredibly weak rocket engine powered by stellar radiation. The effect has been observed and measured for numerous asteroids in our solar system, causing gradual changes in their orbits over millions of years. The mathematical analysis was straightforward. Given the object's estimated size, mass, and thermal properties, the Yarkovsky effect would indeed create a small force. But when researchers calculated the magnitude of this force, they discovered it was orders of magnitude too weak to account for the observed deceleration. The effect would need to be hundreds of times stronger than physically possible to explain what we were seeing. Furthermore, the Yarkovsky effect depends critically on the object's rotation and thermal properties. The force direction changes based on how quickly the object spins and how efficiently it absorbs and radiates heat. The steady, consistent nature of our visitor's deceleration suggested a force that remained constant in both magnitude and direction, characteristics incompatible with the variable thermal dynamics that drive the Yarkovsky effect. The fourth investigation examined magnetic field interactions. Could the object be electrically charged, interacting with the sun's magnetic field, or the charged particles of the solar wind? In principle, a charged object moving through a magnetic field experiences forces that could alter its trajectory. Radio telescopes scanned for any electromagnetic emissions that might indicate electrical activity around the visitor. Plasma physicists modelled potential interactions between a charged object and the local space environment. The results were consistently negative. No radio emissions suggested electrical charging. No plasma disturbances indicated magnetic field interactions. The object appeared electromagnetically inert, moving through space without creating the telltale signatures that would accompany significant magnetic forces. Even if such interactions were occurring, the mathematics proved problematic. The forces generated by magnetic field interactions at the distances involved would be far too weak to produce the observed deceleration. The object would need to carry an impossibly large electrical charge or encounter magnetic fields millions of times stronger than anything measured in our solar system. The Fifth Avenue explored tidal forces from nearby stellar systems. Gravity never stops acting, even across the vast distances between stars. Could the gravitational influence of Proxima Centauri, Alpha Centauri, or other nearby stellar systems be tugging on our visitor, gradually slowing its motion through some complex gravitational interaction? The calculations were precise but discouraging. At the distances involved, even the closest stars exert gravitational forces that are vanishingly small compared to what would be needed to explain the observed deceleration. The visitor would need to be passing within a few astronomical units of a massive star to experience significant gravitational effects, but no such stars exist anywhere near its trajectory. Moreover, gravitational forces typically create complex variable effects as objects move through changing gravitational fields. The steady, linear nature of the deceleration we observed was incompatible with the chaotic gravitational environment that exists between stellar systems. As each explanation failed, the scientific community was forced to confront an uncomfortable possibility. Perhaps they were looking at the problem incorrectly. The assumption underlying all these investigations was that some natural force or mechanism was acting upon the visitor to slow it down. But what if that assumption was wrong? What if the deceleration wasn't being done to the object, but by it? This possibility led to a sixth and more unsettling line of inquiry: measurement artifacts and observational errors. Could the apparent deceleration be an illusion created by systematic errors in observational data processing? The measurements required extraordinary precision, detecting velocity changes of centimeters per second across billions of kilometers of space. Perhaps the instruments were introducing subtle biases, or the data reduction algorithms were creating false signals. Multiple independent observatories were enlisted to verify the measurements. Different telescopes, different instruments, different analysis teams all converged on the same conclusion: the object was indeed slowing down. The statistical significance of the measurements far exceeded the threshold for observational error. The deceleration was real, measurable, and reproducible. Cross-checks with known objects in similar trajectories confirmed that the instruments were functioning correctly. Reference stars showed no anomalous motion. Other asteroids and comets behaved exactly as predicted. Only this single visitor exhibited the impossible behavior. The elimination of measurement error as an explanation left astronomers in an unprecedented position. They had exhausted every conventional mechanism that could account for what they were observing. The failure of natural explanations to account for the visitor's behavior created a profound sense of unease within the scientific community. Science progresses by explaining observations through known physical principles, but here was a phenomenon that seemed to exist outside those principles entirely. Some researchers proposed more exotic mechanisms, interactions with dark matter, encounters with primordial black holes, effects of modified theories of gravity that might operate differently in the depths of interstellar space. But each of these explanations required invoking physics that remained hypothetical, forces that had never been directly observed, phenomena that existed at the very edge of theoretical possibility. The most uncomfortable aspect of the failed explanations wasn't just that they didn't work, it was how consistently they didn't work. Natural phenomena typically leave complex, messy signatures. Multiple mechanisms usually contribute to observed effects. But the deceleration of our visitor was remarkably clean, steady, and purposeful in its characteristics. It looked, in other words, exactly like what we might expect from something artificial. This realization forced astronomers to confront a possibility that challenged not just their understanding of physics, but their assumptions about the nature of space itself. If natural forces couldn't explain what they were seeing, then perhaps what they were seeing wasn't entirely natural. The systematic failure of every conventional explanation had cleared away the comfortable certainties of known physics, leaving behind a mystery that demanded new thinking. Either our understanding of the forces that operate in interstellar space was fundamentally incomplete, or we were witnessing something that operated according to different rules entirely. Rules that implied intention, control, and purpose, rather than the blind operation of natural law. As our visitor continued its impossible journey, steadily losing speed in defiance of every known principle of celestial mechanics, it carried with it more than just the puzzle of its own behavior. It carried the weight of a question that no amount of conventional science seemed able to answer. What kind of phenomenon could travel between the stars and choose to slow down when it reached our solar system? The answer to that question would require us to venture beyond the comfortable boundaries of natural explanation and consider possibilities that were far more provocative and far more unsettling than anything physics had prepared us to contemplate. There are moments in the history of astronomy when the universe reveals its secrets not through what we can see, but through what we cannot. When invisible forces make themselves known by their effects on the visible world, bending light and matter in ways that whisper of hidden truths waiting in the cosmic shadows. Perhaps the most famous such moment came in the 19th century, when French mathematician Urbain Le Verrier sat at his desk with nothing but pencil, paper, and the elegant equations of celestial mechanics. He was studying a problem that had puzzled astronomers for decades. The planet Uranus wasn't behaving properly. Uranus followed an elliptical orbit around the Sun, as expected, but its path showed tiny deviations that couldn't be explained by the gravitational influence of known planets. Something was tugging at Uranus, pulling it slightly off its predicted course, but that something remained invisible to every telescope pointed toward the outer reaches of the solar system. Le Verrier made a bold assumption. The invisible influence was another planet, massive enough to perturb Uranus's orbit, but too distant and dim to be easily detected. Using only mathematics, he calculated where this hypothetical world must be located, how massive it must be, and precisely where telescopes should look to find it. On September 23, 1846, German astronomer Johann Galle pointed his telescope toward the coordinates Le Verrier had specified. Within an hour, he found Neptune, exactly where the mathematics had predicted it would be. The discovery was more than just the finding of a new planet. It was proof that invisible objects could reveal themselves through their gravitational influence on visible matter. The universe, it seemed, contained hidden depths that could be explored not through direct observation, but through careful analysis of the subtle ways they shaped the cosmos around them. This principle of detection through influence has guided astronomical discovery ever since. We found black holes by watching stars orbit invisible companions. We've mapped dark matter by observing how its gravity bends the light from distant galaxies. We've discovered exoplanets by measuring the tiny wobbles they induce in their parent stars. Could the same principle explain our visitor's impossible deceleration? The hypothesis was both elegant and unsettling. Perhaps our mysterious traveller was encountering something massive but invisible, something that was gravitationally slowing its passage through what we had assumed was empty space. The first candidate was dark matter, that mysterious substance that comprises 85% of all matter in the universe, yet interacts with ordinary matter almost exclusively through gravity. Dark matter typically exists in vast diffuse halos around galaxies, but computer simulations suggest it could occasionally form dense clumps or concentrations that might affect passing objects. Could our visitor be passing through such a concentration? The mathematics were tantalizing. A sufficiently dense clump of dark matter could indeed exert gravitational forces strong enough to slow an interstellar object. Unlike ordinary matter, dark matter wouldn't emit light or heat, making it effectively invisible to conventional telescopes. It would reveal itself only through its gravitational influence, exactly what we seem to be observing. But the requirements were daunting. The dark matter concentration would need to be extraordinarily dense, millions of times denser than the cosmic average, yet somehow remain stable and localized in the space near our solar system. Current models of dark matter structure formation suggested that such configurations were possible, but extremely rare. More problematically, if such a massive dark matter clump existed in our cosmic neighborhood, its gravitational effects should be detectable in other ways. It should perturb the orbits of comets in the outer solar system, create subtle gravitational lensing effects on background stars, perhaps even influence the trajectories of spacecraft in the outer reaches of our planetary system. Searches for these additional signatures proved frustratingly negative. No unexplained perturbations in cometary orbits, no gravitational lensing anomalies, no spacecraft trajectory deviations. If a dark matter concentration existed, it was affecting only our visitor, a selectivity that seemed to defy the universal nature of gravitational interaction. The second candidate was even more exotic, a primordial black hole. These hypothetical objects formed in the early universe from extremely dense regions of matter could range in mass from microscopic to stellar scales. A primordial black hole with the mass of a large asteroid, perhaps a few billion tons, would be completely invisible to direct observation, yet massive enough to gravitationally influence passing objects. The gravitational signature would be distinctive. Unlike the broad, distributed influence of a dark matter clump, a black hole would create sharp, localized gravitational effects that varied dramatically with distance. As our visitor approached the black hole, it would experience increasing deceleration, then acceleration as it passed the closest point, followed by deceleration again as it receded. But the observational data showed no such variation. The deceleration remained remarkably steady and consistent throughout the visitor's passage, characteristics more compatible with a distributed mass than a point source like a black hole. Moreover, the existence of primordial black holes in our solar neighborhood would require an extraordinary coincidence. These objects, if they exist at all, should be extremely rare in any given volume of space. The probability that one would happen to lie directly along the trajectory of an interstellar visitor seemed vanishingly small. The third possibility was perhaps the most conventional yet equally puzzling: a rogue planet or brown dwarf wandering invisibly through interstellar space. Planets can be ejected from their birth systems through gravitational interactions, becoming nomadic worlds that drift between the stars without the warming light of a parent sun. Brown dwarfs, failed stars too small to ignite nuclear fusion, could similarly wander through space, massive enough to gravitationally influence other objects yet too dim to be easily detected at interstellar distances. The gravitational calculations were straightforward. A rogue planet with several times the mass of Jupiter, positioned at the right distance and orientation relative to our visitor's trajectory, could potentially create the observed deceleration. The object would need to be roughly Earth-sized to remain undetected by infrared surveys, yet massive enough to exert significant gravitational influence, a combination that pushed the boundaries of planetary physics but remained theoretically possible. But again, the timing seemed impossibly convenient. What were the odds that our visitor would encounter a rogue planet precisely as it passed through our solar system? The vast emptiness of interstellar space makes such encounters extraordinarily unlikely, comparable to two specific grains of sand meeting in a desert that spans continents. More troubling still, multiple surveys of the sky in infrared and radio wavelengths had failed to detect any massive objects in the relevant region of space. Even a cold, dark planet should emit some thermal radiation that would be detectable by sensitive instruments. The absence of such signals suggested that if a rogue planet was responsible for the deceleration, it was somehow even more invisible than theoretical models predicted. As astronomers explored each possibility for hidden gravitational influence, A pattern emerged that was as puzzling as the original mystery. Every scenario that could potentially explain the visitor's deceleration required extraordinary circumstances. Impossibly dense dark matter concentrations, perfectly positioned primordial black holes, conveniently located rogue planets that somehow remained undetectable despite extensive surveys. The mathematics of each scenario worked in isolation, but the probabilities were so small as to strain credibility. It seemed as though the universe would need to conspire in remarkably specific ways to place exactly the right kind of invisible mass in exactly the right location at exactly the right time to affect our visitor's trajectory. This realization led to an even more unsettling possibility. Perhaps the timing wasn't coincidental at all. If our visitor was indeed encountering something massive and invisible, the fact that this encounter was happening precisely as the object passed through our solar system might not be an accident of celestial mechanics. It might be evidence of something more purposeful, a gravitational influence that was somehow connected to our cosmic neighborhood, positioned or timed to affect objects that ventured into our local space. The implications of this possibility pushed the boundaries of conventional astronomical thinking. It suggested that the space around our solar system might not be as empty or as random as we had assumed. Perhaps there were structures or objects in our cosmic vicinity that remained hidden from our telescopes yet exerted influence on visitors from other stellar systems. But even this exotic scenario raised more questions than it answered. How could such objects remain so perfectly hidden? Why would they affect only certain visitors and not others? What kind of natural process could create such precisely positioned gravitational influences? As each attempt to explain the visitor's deceleration through invisible gravitational forces encountered new layers of improbability, astronomers found themselves confronting a possibility that challenged their fundamental assumptions about the nature of space itself. Perhaps the force slowing our visitor wasn't gravitational at all. Perhaps it wasn't natural. Perhaps what we were witnessing was evidence of something that operated according to entirely different principles. Principles that implied not just mass and gravity, but intention and control. The systematic failure of gravitational explanations, like the failure of conventional forces before them, was clearing away the comfortable certainties of natural law and revealing something far more provocative underneath. If hidden masses couldn't account for what we were seeing, if the probabilities of natural encounters stretched beyond believability, then we might be looking at evidence of something that was never meant to be explained by natural forces alone. Our visitor's steady, purposeful deceleration was beginning to look less like the random result of cosmic coincidence, and more like the deliberate action of something that possessed the ability to choose its own path through space, something that could travel between the stars and then slow down precisely when it reached our solar system. Not because of what it encountered, but because of what it intended to do. The invisible hand that seemed to be guiding our visitor might not be the blind force of gravity after all. It might be something far more unsettling, the deliberate control of intelligence that had travelled across the cosmic deep to pay us a visit, announcing its presence not through radio signals or obvious displays of technology, but through the simple, impossible act of choosing to slow down when physics said it should speed away. There is something profoundly different about watching an object choose its path through space versus watching it follow the predictable choreography of natural law. When we observe the planets in their orbits, the comets in their elongated journeys, even the chaotic tumbling of asteroids, we see the elegant mathematics of gravity and momentum playing out across cosmic scales. But occasionally, rarely, we encounter something that moves with purpose rather than physics, intention rather than inertia. Our spacecraft are perfect examples of this distinction. When Voyager 1 departed Earth in 1977, it followed a trajectory precisely calculated to take advantage of a rare alignment of the outer planets. It accelerated past Jupiter, using that giant world's gravity to fling itself towards Saturn. At Saturn, it used another gravitational assist to redirect toward the edge of the solar system. Each course change was deliberate, planned, executed with the precision that only intelligent control can provide. But Voyager also demonstrated something else: the unmistakable signatures of artificial propulsion. When the spacecraft needed to adjust its course or orientation, it fired small thrusters that left distinctive traces in its trajectory. Sudden, precisely timed changes in velocity that stood out clearly against the smooth curves of gravitational influence. More recently, our New Horizons probe provided another example of controlled space travel. After its encounter with Pluto, the spacecraft used its remaining fuel to alter course toward a small Kuiper Belt object called Arrokoth. The maneuver required careful calculation of thrust duration, direction, and timing. The resulting trajectory change was subtle but unmistakable, a clear deviation from the path that gravity alone would have dictated. These examples from our own space exploration reveal the characteristic signatures of controlled motion: precision, purposefulness, and the ability to make trajectory adjustments that serve specific goals rather than follow natural law. Which brings us to the unsettling question that our visitor's behaviour has forced us to confront. What if the deceleration we're witnessing isn't the result of natural forces at all, but evidence of similar control? The more closely astronomers examined the visitor's trajectory, the more its behaviour resembled artificial propulsion rather than natural phenomena. The deceleration was remarkably steady and consistent, exactly what we might expect from a controlled thrust system operating at low but constant power. Natural forces tend to create variable, chaotic effects as objects encounter changing conditions along their paths. But our visitor's slowdown followed an almost linear pattern, as if guided by a navigation system maintaining precise control over velocity changes. The energy requirements for such controlled deceleration were staggering yet not impossible. Calculations suggested that slowing an object of the visitor's estimated mass would require energy equivalent to several nuclear power plants operating continuously for months. By the standards of our current technology, such energy expenditure would represent a massive engineering undertaking. But for a civilization capable of interstellar travel, it might be merely routine. More intriguingly, the timing and location of the deceleration suggested sophisticated planning. The visitor had travelled for potentially thousands of years across the void between stars, maintaining constant velocity throughout its journey. Only when it entered our solar system, only when it came within range of our telescopes and detection capabilities, did it begin to slow down. This timing could hardly be coincidental. If the deceleration was artificial, it implied awareness of our technological capabilities, knowledge of our observational methods, perhaps even deliberate intention to be noticed. The visitor wasn't simply passing through our cosmic neighbourhood. It was performing for an audience it knew would be watching. The precision of the maneuver was equally telling. The deceleration was perfectly calibrated to be detectable by our instruments, yet subtle enough to avoid immediate recognition as artificial. Too little slowdown, and we might have missed it entirely, attributing small velocity variations to measurement error. Too much, and the artificial nature would have been immediately obvious, perhaps triggering responses that an observing intelligence might prefer to avoid. Instead, the visitor chose a middle path, obvious enough to puzzle us, subtle enough to maintain ambiguity about its true nature. This calculated ambiguity suggested something even more unsettling than mere artificial propulsion. It implied intelligence that understood not just the physics of interstellar travel, but the psychology of first contact, an intelligence that preferred observation to announcement, surveillance to communication. The comparison with our own exploration methods was instructive. When we send probes to other planets, we don't usually announce our arrival with dramatic displays of technology. Instead, we approach quietly, orbit at safe distances, observe without interfering. We gather data before making our presence known, if we choose to make it known at all. Could our visitor be following a similar protocol? The possibility that we were being observed, studied, by an intelligence from another star system created a profound shift in how astronomers viewed the deceleration data. Every measurement became potentially significant, not just as evidence of unusual physics, but as communication from visitors who had travelled across the cosmic deep to examine our world. Radio telescopes around the globe turned toward the visitor, scanning across electromagnetic frequencies for any signal that might indicate artificial origin. The searches were comprehensive but yielded only silence. No radio transmissions, no laser communications, no obvious attempt at contact through technological means. But perhaps the silence itself was meaningful. An intelligence advanced enough to travel between stars would likely understand that overt communication might trigger unpredictable responses from a species still confined to a single world. History suggests that first contact between civilizations with vastly different technological capabilities rarely proceeds smoothly. The visitor's restraint might represent wisdom born of experience, or caution born of observation of our own behavior. The deceleration itself might be the communication. Think of it as a cosmic calling card, a demonstration of technological capability that couldn't be mistaken for natural phenomena, yet subtle enough to avoid panic or premature interaction. The visitor was showing us that it possessed the ability to control its motion in ways that defied our understanding of physics, while simultaneously demonstrating restraint in how it chose to use that ability. This interpretation suggested a level of sophistication that was both reassuring and deeply unsettling. Reassuring because it implied intelligence rather than mere technology, deliberate choice rather than automatic response. Unsettling because it meant we were being evaluated by minds that operated according to principles we couldn't fathom, using capabilities we couldn't match. The behavioral analysis became even more provocative when astronomers examined the visitor's approach trajectory in detail. The object hadn't simply wandered into our solar system along a random path. Its approach angle and velocity were optimized for maximum observational opportunity, passing close enough to be easily detected and tracked, yet far enough away to avoid any gravitational complications with our planets. The trajectory resembled nothing so much as a reconnaissance flight, carefully planned to gather maximum information while maintaining safe distance from potentially unpredictable subjects. If this interpretation was correct, then our visitor wasn't just passing through our cosmic neighborhood. It was conducting a survey, a systematic examination of our solar system, and perhaps our civilization itself. The deceleration wasn't an accident or malfunction. It was a deliberate extension of the observation period, allowing more time to study whatever had attracted its attention. The implications rippled outward like waves from a stone dropped in still water. If our visitor was artificial, if its behavior indicated intelligence and purpose, then we were confronting the reality that we were not alone in the universe. More than that, we were confronting the possibility that other intelligences were actively studying us, evaluating our development, perhaps making decisions about our future based on what they observed. The visitor's restraint in communication might not reflect caution about our reactions. It might reflect judgment about our readiness for contact with intelligence that operated on cosmic rather than planetary scales. This possibility transformed every aspect of the visitor's behavior from puzzle to message. The steady deceleration became evidence of technological capability. The precise timing became demonstration of awareness. The calculated subtlety became indication of sophisticated evaluation protocols developed by minds that had learned to approach other civilizations with careful deliberation. But perhaps most unsettling of all was the realization that if our interpretation was correct, the visitor's mission was likely not complete. Objects that slow down in space are objects that intend to linger, to observe, to accomplish goals that require extended presence rather than brief encounter. Our mysterious traveller might not be passing through our solar system at all. It might be arriving. The implications of that possibility would challenge every assumption we had made about our place in the universe, our isolation in the cosmic deep, and our readiness for contact with intelligence that had mastered the vast distances between stars. We were no longer simply observing an anomalous object. We were potentially being observed in return by minds that possessed capabilities we could barely imagine, and motivations we couldn't begin to understand. In the silence of space, our visitor continued its impossible deceleration, gradually extending its stay in our cosmic neighborhood, while we watched and wondered, and slowly came to terms with the possibility that the age of human isolation in the universe might be coming to an end. Not through our own expansion into space, but through the arrival of visitors who had chosen to notice us at last. Long before we possessed telescopes sophisticated enough to track objects across interstellar distances, long before we understood the mathematics of orbital mechanics or the physics of space travel, human beings have been watching the sky with careful, patient eyes. Our ancestors were observers of extraordinary precision. Without the distractions of artificial light or the assumption that the heavens were merely decorative, they mapped the movements of planets, recorded the appearances of comets, and noted with meticulous care anything that deviated from the expected patterns of celestial motion. They understood, in ways we sometimes forget, that the sky was not a static backdrop but a dynamic theatre where stories unfolded across timescales that spanned generations. They watched for portents and signs, for visitors and wanderers, for anything that might suggest the heavens were paying attention to the small dramas playing out on the world below. And sometimes, according to their carefully preserved records, they witnessed things that shouldn't have been possible. In the ancient texts of many cultures scattered like stars across the constellation of human memory, we find accounts of celestial objects that behaved in ways that challenge our understanding of natural law. Stars that paused in their journeys, wandering lights that slowed their passage across the sky, celestial visitors that lingered longer than the mathematics of motion should have allowed. For centuries, scholars have interpreted these accounts as mythology, as primitive attempts to explain natural phenomena through supernatural intervention. But what if we've been reading them incorrectly? What if some of these ancient observations were accurate records of events that we're only now beginning to understand? The most famous of these accounts appears in the Hebrew Bible in the book of Joshua, where we read of a day when the sun stood still in the sky during a crucial battle. The text describes how Joshua commanded the sun to remain motionless, and the sun stood still and the moon stayed until the people had avenged themselves upon their enemies. For generations, this passage has been interpreted as either metaphorical or miraculous, a divine intervention that suspended the normal operation of celestial mechanics for the duration of a single day. But what if it was neither metaphor nor miracle? What if it was an accurate description of something extraordinary that ancient observers witnessed in their sky? The account becomes even more intriguing when we examine similar stories from other cultures of the same general time period. Chinese astronomical records from the Shang dynasty describe occasions when guest stars appeared in the sky and behaved in unexpected ways, sometimes moving slowly across the heavens before stopping entirely, sometimes brightening and dimming in patterns that suggested deliberate signals rather than natural stellar processes. These Chinese observations are particularly significant because they come from a civilization that maintained remarkably accurate astronomical records for over 3,000 years. Chinese astronomers tracked the movements of planets, predicted eclipses, and recorded the appearances of novae and supernovae with precision that modern science has verified and admired. When these careful observers noted celestial objects that deviated from expected behaviour, we should perhaps take their accounts more seriously than we have. The Star of Bethlehem presents another puzzle that has captivated scholars for 2 millennia. The Gospel of Matthew describes a star that guided wise men to the location of Jesus' birth, describing how the star, which they saw in the east, went before them till it came and stood over where the young child was. The language is precise and observational. The star moved, then stopped. It went before them during their journey, suggesting controlled motion rather than the random wandering of a comet or the predictable progression of a planet. Most tellingly, it stood over a specific location, behaviour that implies the ability to position itself with purpose rather than simply follow the gravitational laws that govern natural celestial objects. Astronomers have proposed numerous explanations for the Star of Bethlehem. Planetary conjunctions that would have appeared as unusually bright lights, comets that coincidentally appeared during the relevant time period, even supernovae that might have blazed briefly in nearby star systems. But none of these natural phenomena explain the controlled motion described in the text, the apparent ability of the star to lead travellers along a specific route and then halt above a particular destination. What if the ancient observers were describing exactly what they saw, a celestial object that possessed the ability to control its own motion? Indigenous astronomical traditions from around the world contain similar accounts of sky objects that behaved in ways that challenge natural explanation. Native American stories speak of wandering stars that changed their behaviour when observed by human beings, slowing their passage across the sky as if aware they were being watched. Some traditions describe lights in the sky that would approach the Earth, hover for extended periods, then depart along paths that defied the normal motion of celestial objects. Aboriginal Australian cultures, with astronomical traditions that stretch back tens of thousands of years, tell dreamtime stories of sky spirits that moved differently from ordinary stars. These spirits could travel rapidly across great distances, then pause their journeys to observe events unfolding on the Earth below. The descriptions bear striking resemblances to our modern, observations of objects that seem to possess agency and intention rather than simply following the blind forces of gravity and momentum. The consistency of these accounts across different cultures and time periods is remarkable. Separated by continents and centuries, isolated civilizations independently recorded observations of celestial objects that seem to possess to control their own motion, to accelerate, decelerate, and change direction in ways that suggested intelligence rather than natural law. Perhaps most intriguingly, many of these ancient accounts describe celestial visitors that announce their presence through behavior rather than appearance. Unlike comets, which display dramatic tails and obvious visual spectacle, these mysterious objects made themselves known through motion, through the simple but impossible act of choosing to move differently than physics would predict. The pattern is hauntingly familiar to anyone who has studied our current visitors' behavior. Modern astronomy has taught us to be skeptical of ancient accounts that seem to describe supernatural events. We've learned that many historical miracles can be explained through natural phenomena that ancient observers didn't understand: eclipses, meteor showers, planetary alignments, and other predictable celestial events. But our current encounter with an object that defies conventional physics forces us to reconsider this skepticism. If we're witnessing something that shouldn't be possible according to our understanding of natural law, then perhaps our ancestors witnessed similar impossibilities and preserved their observations in the only frameworks available to them. Stories of divine intervention, myths of supernatural visitors, legends of sky spirits with agency and purpose. The reinterpretation of these ancient accounts suggests a possibility that is both humbling and unsettling. We might not be the first generation of human beings to encounter visitors from other star systems. If our current visitor represents evidence of intelligence that has mastered interstellar travel, then the consistent reports of anomalous celestial behavior throughout human history might represent a pattern of contact that spans millennia. Perhaps other civilizations have been observing us for far longer than we've imagined, occasionally revealing their presence through demonstrations of impossible motion, testing our observational capabilities and our readiness for more direct interaction. This possibility transforms our understanding of both ancient history and modern astronomy. The myths and legends that we've dismissed as primitive superstition might be humanity's oldest scientific records, careful observations of phenomena that challenged ancient understanding just as our current visitor challenges ours. The implications extend beyond historical curiosity into profound questions about the nature of contact between civilizations. If the pattern of ancient observations reflects real encounters with non-terrestrial intelligence, then such intelligence has been remarkably consistent in its approach. Subtle demonstration of capability rather than overt communication, careful observation rather than immediate contact, patient evaluation spanning centuries or millennia. Our current visitor might represent not first contact, but the latest in a long series of evaluations conducted by minds that operate on timescales we can barely comprehend. The ancient accounts suggest that whatever intelligence might be behind these visitations has been extraordinarily patient and cautious in its approach to humanity. Rather than announcing itself dramatically or attempting immediate communication, it has chosen to reveal itself gradually, allowing human civilization to develop its own understanding of the cosmos before presenting evidence that challenges that understanding. This pattern of gradual revelation implies wisdom and restraint that should perhaps comfort us more than it unsettles us. An intelligence capable of interstellar travel could presumably make contact in whatever manner it chose. The fact that it has consistently chosen subtle demonstration over dramatic announcement suggests consideration for our development and perhaps respect for our autonomy as a developing civilization. But it also suggests that we might be approaching a threshold in this ancient pattern of contact. Our technological capabilities have advanced to the point where we can detect and analyze the subtle signatures of controlled motion that our ancestors could only describe in mythological terms. We're no longer limited to naked eye observations and oral traditions. We possess instruments capable of measuring impossibly small changes in velocity across vast distances of space. Perhaps our current visitor represents recognition of this technological threshold, an acknowledgement that humanity has developed sufficient observational capability to detect and study evidence of non-natural phenomena in space. The deceleration we're witnessing might be calibrated precisely to our current technological abilities designed to be detectable by our instruments, while maintaining the same careful ambiguity that has characterized these encounters throughout history. If this interpretation is correct, then we're witnessing not just an astronomical anomaly, but a moment of transition in humanity's relationship with intelligence that has been watching us develop across the long arc of our civilization. The myths of slowing stars might be humanity's oldest records of contact with minds that journey between the worlds, patient observers who have watched our species grow from primitive sky watchers to a civilization capable of detecting the impossible signatures of controlled motion across interstellar space. And our current visitor might be their way of acknowledging that we've finally developed the capability to recognize their presence for what it truly is. In the beginning was motion. Long before there were stars to burn, planets to orbit, or comets to trace their ancient paths across the cosmic dark, there was the fundamental dance of existence itself. Particles moving through space, energy flowing from one state to another, the very fabric of space-time expanding in the grand choreography that began with the Big Bang and continues to this very moment. Motion is not merely a property of the universe, it is the engine of time itself, the force that transforms potential into reality, the fundamental characteristic that separates existence from void. Without motion, there would be no chemistry, no biology, no consciousness to contemplate the strange beauty of a cosmos in perpetual dance. Everything moves. Electrons orbit atomic nuclei in probability clouds of constant motion. Molecules vibrate and tumble in the restless ballet of thermal energy. Planets wheel around their stars in elliptical paths that have remained unchanged for billions of years. Stars themselves race through space at hundreds of kilometers per second, carrying their retinues of worlds through the galaxy's spiral arms. And galaxies, those vast islands of stars and darkness, rush away from each other in the expanding vastness of space-time itself. This universal motion follows laws so fundamental that we have built our entire understanding of reality upon them. The conservation of momentum tells us that objects in motion will remain in motion unless acted upon by external forces. The constancy of physical laws assures us that the same principles governing motion on Earth apply equally in the furthest reaches of intergalactic space. For centuries, these laws have provided the bedrock of predictability that makes science possible. We can calculate the position of planets decades in advance, predict the return of comets across generations, and navigate spacecraft to distant worlds with precision measured in meters across billions of kilometers of space. The universe, for all its complexity and grandeur, has always been fundamentally comprehensible because motion itself is comprehensible. Until now. Our mysterious visitor has done something that shouldn't be possible in a universe governed by physical law. It has chosen to slow down without apparent cause, defying the fundamental principle that objects in motion stay in motion unless acted upon by external forces. This violation of natural law represents more than just an astronomical puzzle. It challenges the very foundations of our understanding of reality itself. When an object spontaneously decelerates in the vacuum of space, it forces us to confront the possibility that the universe is not entirely predictable, not completely governed by the mathematical laws we've discovered. It suggests that there might be phenomena operating according to principles we haven't yet discovered, or perhaps can't discover through conventional scientific methods. The implications ripple outward like gravitational waves from a cosmic collision, disturbing every assumption we've made about the nature of space, time, and causality. If our visitor is behaving according to natural forces we don't understand, then our models of physics are fundamentally incomplete. The equations that have guided us to the Moon, to Mars, to the edge of the solar system itself might be special cases of more general laws that operate on scales or in ways we've never encountered. This possibility is both humbling and exciting. Throughout history, apparent violations of natural law have often preceded revolutionary advances in scientific understanding. The strange orbit of Mercury led to general relativity. The mysterious behavior of blackbody radiation opened the door to quantum mechanics. Perhaps our visitor's impossible deceleration will similarly point the way toward new physics that expands our understanding of how the universe really works. But there is another possibility, one that challenges not just our science but our fundamental assumptions about our place in the cosmos. What if the deceleration we're witnessing isn't natural at all? The systematic failure of every conventional explanation, the precise timing of the slowdown, the calculated subtlety of the effect all point toward a conclusion that is as unsettling as it is profound. We might be observing evidence of intelligence that has mastered the vast distances between stars. If this interpretation is correct, then our visitor represents something far more significant than a failure of physics. It represents the end of humanity's cosmic isolation, the first confirmed evidence that we are not alone in a universe that spans billions of light years and contains countless worlds. The implications of this possibility extend far beyond astronomy into every aspect of human understanding and experience. For thousands of years, we have wondered whether intelligence exists elsewhere in the universe. We've searched the skies for radio signals, examined meteorites for signs of microscopic life, and launched spacecraft to explore the worlds of our own solar system. But until now, we've found only silence, sterility, and the apparent absence of any intelligence other than our own. Our visitor's behaviour suggests that this absence might have been an illusion created by our own limitations rather than the reality of a lifeless cosmos. If intelligence exists that can travel between stars, then the universe is a far more vibrant and populated place than we've dared imagine. The silence we've interpreted as emptiness might actually reflect the restraint of minds that operate on scales, and according to principles we're only beginning to comprehend. The possibility that we're being observed, studied, by such intelligence forces us to reconsider not just our scientific understanding, but our philosophical assumptions about consciousness, purpose, and meaning in the cosmos. For centuries, human thought has grappled with the apparent conflict between the vastness of the universe and the smallness of human existence. We've wondered whether consciousness is a cosmic accident, a brief flicker of awareness in an otherwise unconscious cosmos, or whether mind and meaning might be fundamental features of reality itself. The discovery of intelligence that has mastered interstellar travel would suggest that consciousness is not an accident, but perhaps one of the universe's most remarkable and persistent creations. It would mean that the cosmos has been developing minds capable of contemplating its own existence across billions of years and countless worlds. This possibility transforms our understanding of humanity's role in the cosmic story. Rather than being isolated observers of a lifeless universe, we might be participants in a vast community of intelligence that spans the galaxy, and perhaps beyond. The questions that have driven human science and philosophy, the nature of reality, the meaning of existence, the possibility of purpose in a vast cosmos, might be questions that countless other minds have contemplated across the deep reaches of space and time. But perhaps most profoundly, the behaviour of our visitor suggests that if such intelligence exists, it approaches other minds with patience, restraint, and perhaps wisdom born of experience with contact between civilizations. The deceleration we're witnessing isn't a dramatic announcement or an obvious attempt at communication. It's a subtle demonstration of capability, carefully calibrated to be detectable yet ambiguous, challenging yet not threatening. It suggests intelligence that understands the delicate nature of first contact between civilizations with vastly different capabilities and perspectives. This restraint might reflect hard-won knowledge about the challenges of interaction between minds that have developed under different stars, according to different evolutionary pressures, with different assumptions about reality and consciousness. The fact that our visitor has chosen to reveal itself through impossible motion, rather than obvious communication, might indicate respect for our autonomy as a developing civilization, allowing us to discover and interpret the evidence according to our own capabilities and readiness. As we continue to track our visitor's impossible journey through our solar system, measuring its steady deceleration and pondering the implications of its behaviour, we find ourselves at a threshold in human understanding. Either we're witnessing new physics that will revolutionise our understanding of how the universe works, or we're observing evidence that we are not alone in that universe. Both possibilities would transform human knowledge and experience in ways that are difficult to fully comprehend. But perhaps the most important transformation is already occurring in how we see ourselves and our place in the cosmic story. Our visitor has shown us that the universe is stranger and more wonderful than we imagined. Whether its impossible behaviour results from undiscovered physics or unimagined intelligence, it has demonstrated that reality itself is far more mysterious and layered than our current understanding suggests. In a cosmos where everything moves according to predictable laws, The presence of something that chooses to slow down represents a fundamental challenge to our assumptions about what's natural and what's possible. It suggests that the universe might be a far more intentional and consciousness-filled place than we've dared to hope. Every clear night, our mysterious visitor continues its impossible journey above our heads, gradually losing speed in defiance of every principle of celestial mechanics we've discovered. Its steady deceleration serves as a constant reminder that reality is deeper and stranger than our models predict, that the cosmos might be populated by minds we're only beginning to detect, and that the age of human isolation in the universe might be drawing to a close. Whether our visitor represents new science or first contact, it has already given us something invaluable: proof that the universe is still capable of surprising us, still harbouring mysteries that challenge our understanding and expand our sense of what's possible in the vast symphony of existence. In the end, the question isn't just what force is slowing our interstellar visitor, but what its presence means for humanity's understanding of motion, meaning, and mind in a cosmos that has revealed itself to be far stranger and more wonderful than we ever imagined. The answer to that question will unfold in the nights and years ahead, as we continue to watch the impossible spectacle of something choosing to break the fundamental rules of motion itself, carrying with it implications that will reshape our understanding of everything we thought we knew about the nature of reality and our place within it. In a universe where everything moves, the discovery of something that chooses to slow down changes everything we believed about the cosmic dance of existence, and perhaps everything we believed about whether we dance alone.